All right, 1 second. We should be live. I forgot to double check though before I unmuted. So I'm just blindly committing to this. So 1 second. Make sure GLOBEBUSTERS is live.
I see it live on my end.
Awesome. All right. Hello and welcome everyone to season 14, episode 3 of GLOBEBUSTERS. We're joined today by Shane, Stone, Cami, and Karen. We're going to be going over the celestial theodolite, but before I begin, we'll see how everyone's doing this week. Shane, how are you, my man?
Fantastic. Hanging in there. Thanks for asking, dude.
Awesome. Stone G, how are you, good sir?
Oh, good. Good to be here. Up and happening.
Nice.
Indeed.
Karen, how are you?
Fantastic. Happy to be here.
Nice. Awesome. And Cami, hope you're doing just as good.
Oh, you guys are all doing great. I'm a little bit sideways today. It's just the way it is. Some weeks are like that. So think pretty
Well,
good, but yeah, just a wee bit sideways.
For those of you who don't know, Cami's committed to a hilarious surveying bit about being perpendicular to the gravitational potential of the geoidal model that she's chosen to believe in. So there's I respect your decision on that, Cami, but hopefully this presentation will help bring you back to, down is down, Cami. So
I know, but we have like there's
back.
inertial planes on the quad. We do have inertial planes running in like possibly multiple directions, and so we are testing the theory that we all are sideways and not really up and down. So
well, the dead giveaway is when your drink falls off the table sideways. Just look at it and it goes. Whoosh.
Oh, but it's not. I mean, we are. Yeah, we are. Yeah. It's
Awesome.
working for me, guys. It's working for me. I'm not saying it's going to work for everybody, but it is working for me.
All right. So to introduce us a little bit to the subject, it's one of my new favorites, and it's you can kind of classify it if you guys have ever looked into something called Archaeoastronomy. Have you guys ever heard of that?
Archaeoastronomy?
Yeah, it sounds made up, doesn't it? But it's an actual term and field of study.
Is this how the ancients looked at the stars and how they measured, or how they tell or how it's written? Tell us what we're about structures and.
Yeah, you nailed it. So they would build terrestrial structures that would intersect with celestial ones. So they would measure the sun's position rising and setting throughout the year. Once.
Jinkies, it's the cops.
Yeah.
And, it's a real thing. It's a real thing. The Sphinx does point directly east, and keep going.
And because the bodies return to their positions every year, they would make calendars and things based off of these terrestrial markers. So with that, we get into dynamics and kinematics, because we're told that we're spinning, rotating, and going around the solar system and all these things. But for in certain scenarios, for the terrestrial and celestial things to line up, the Earth has to be stationary, and the motion, or the apparent motion, between the two bodies has to be between the sun and the stars. The Earth can't be the cause of it. Otherwise, these structures that have been built wouldn't align with the sun's position every year throughout the year. It would be they would eventually fall out of sync. So we get into a scenario where, by using terrestrial intersections with the celestial, we can determine, like, okay, we're not moving. But if you just go by looking at it alone, you can't tell, because kinematics and motion, all motion's relative in kinematics. So this is like a really cool, like the thing that Stone did with the measuring the angles to the shadows and showing that the vertex doesn't invert. You can make certain geometric there's certain geometric implications that come along with that, and that only comes with the terrestrial and celestial intersections, because just looking at it alone, you can't tell. So we're going to get into something called the celestial theodolite, which I'll screen share now.
Ion in the chat there, he had the greatest term. He took a second shot at it. The term was ethno-archaeopsychopharmacological astronomy. Good
That-
one.
Yep, that's the advanced one.
Dude, I like sidereal surveyor. And there's astronomers plumb bob. There's a couple other names you can use for the celestial theodolite because to show it is a made up concept, right? So you can call it whatever you want.
Yeah, so conceptually, the celestial theodolite is using the intersection of celestial bodies with the terrestrial. So we have the celestial body of the star that we see, the starlight, and we have the terrestrial body, a mountain peak. And because we know the mountain peak's elevation relative to our location and the distance apart from us, we can do some basic trigonometric functions to get some angles, and we can do some predictions based on when the starlight will be blocked by the mountain. Because if we live on a flat Earth, then the mountain won't have any actual physical deviation. Like its optical deviation might, it might look like it's lower, but that's just optical. Physically, the star will be higher, so it'll get blocked by the mountain at a different time than when than if the Earth is a globe, because the mountain peak will actually be lower physically because you're tilted away. So there's going to be some like the angular difference isn't just optical; it's physical. So the star will be able to get lower before it gets occluded. So it gets a different. It'll be that'll correspond to a completely different time.
That's the crux of the argument, though, right? Is that bottom of obstruction? They've always said it's geometric and physical and Earth curve. So this is the ultimate test of that. If we're saying it's optics based and it just compresses optically as angles scale up, versus no, it's covered by physical Earth curve. This is the only way I've come across to adequately differentiate.
Right, and it's so important too because with how refraction works, if there's refraction on this side of the mountain and refraction on this side of the mountain, well, once the source of light is physically below and no longer visible for this lad over here on the other side, the refraction between the mountain peak and the observer is not relevant at all. So it doesn't matter what optical angle you would stop seeing the star. It only matters what time you stop seeing it, because the whole entire globe is built on the latitude and longitude system, and the latitude and longitude system converts your local time into where the positions of the stars are in comparison to where they once were. So angles equal time. So anytime you see an angle to a star, that also corresponds to a specific time in which that star will be there based on where that star once was on the vernal equinox.
Which is the basis of CellNav, as it were, right? Between the two models anyway. And the whole purpose of how you get ground positions as well. The relationship between terrestrial and celestial right there.
Absolutely. The whole point of having the celestial and terrestrial spheres is to convert angles into time. Previous to this, they did rumline navigation, which is just straight lines to a known location, and then they would adjust their bearing and continue on, get to that location, and then continue on to adjust from there. So this system is entirely dependent on using a fictitious observer at the center to relate all the positions of time throughout the day to positions of stars in the celestial sphere, which is bound to the old terrestrial sphere. But yeah, with that though, we can do some trig functions, and we can get some predictions here for what the flat Earth would predict and what the globe would predict in terms of physical intersection timings. Does anyone have any questions so far about the process or true positions of stars or appearance or anything like that?
Just to be clear for the people who have never seen this before, the math that you're currently showing with the triangle that's just on here all by itself, this is the flat Earth trig quote, that there is nothing in this image currently to show the difference between the two scenarios, that the rise here of 2227 meters is what we're looking at with a flat Earth, and the horizontal is brought straight from the observer, and then there's a raw rise up to the peak. And that the globe Earth is asserting that because there is drop over distance, that this won't actually be 2227 in the globe Earth scenario, and would hence yield a different time of occlusion here. So we're going to see that in the later math, I'm sure.
Yep.
Oops,
Yep.
and thank you. I stepped away just a second and was watching, but I wanted to say thank you, Stone, for always taking it back for people that haven't watched, because I think sometimes we forget in the middle of things. So I love that you did that and overviewed it.
Absolutely. So before we continue on, we're going to go over some terminology real quick regarding a triangle in geometry. So in geometry, a tangent is the intersection line with a curve. So you can look at that here. The tangent would be right here where this straight line intersects with this curved line. And the way that we're relating it for trigonometry, it is the ratio of the side of the angle we know or want to know over the adjacent side to that angle. So in other words, we have two functions we could do. We could input two units here. So we have two numbers that we can get an angle, or we can put in, or we could do the angle in one of these numbers and get the other one. So that's how it works. So whatever number we get out of this process, we can actually derive what distance the elevation would have had to have been to cause that occlusion to get that angle. And then we could also derive the distance back based off of that. We could compare the two models based off of which will yield the more accurate results in terms of identifying the position of the observer, because we can construct this in such a way that it's not necessary to tell Stellarium where your observer location is. You can do it by referencing from the peak, and then deriving what your distance would be based off of the occlusion angle and the known elevation of the mountain. So you could do some comparisons here. So you can kind of think of this distance here as your independent variable. You could think of the elevation as your control and the angle as the dependent variable that's dependent on this occlusion timing. And then if that occlusion timing happens to match what the physical elevation prediction would also be for this mountain, then so be it. So we're not necessarily concerned with what the optical measurements of this would be. We're only concerned with the time in which the star is no longer visible. So that's a huge part of the, I mean, that's the entire celestial theodolite process in terms of taking the measurement. We don't care about the optical measurement. We don't need an angle. We just need a time in which the star was no longer visible.
It looks like your
and do
dude's
our
got
comparisons.
a VHS camera there. I'm not sure if they can delineate elevation angles with a VHS camera. It looks like
Well,
he's only able to capture the time.
Well, he knows his frame rate and his time, so he's good to go. And the only reason he's doing it that way is because people told him, "Hey, man, it'd be easier if you get a P900 or a C star." He was like, "No, no, absolutely not." So, okay, let's see here. We did that. Okay, so for how the globe derives what their drops would be, so like Stone was mentioned earlier, how that's not represented here. What they can do is construct an entirely different triangle using the same kind of trig function based off of this equation here to get the drop in meters. So what they would do is they would take the square of the radius of Earth squared plus the distance squared minus the radius, and that'll give them a drop. So in the example of Pikes Peak, it gives them a drop of 200 meters. So we would just change this to 200 meters. And instead of getting an angle of 231, we get an angle of 11 arc minutes, and we would subtract that 11 arc minutes from the 231 to get 217, and that would be our raw. That 217 value would be what the raw globe predicts in terms of where that mountain should be relative to an observer on a ball because of the actual physical elevation difference. So here what we're looking at is what the observer sees, and we have some different positions of the stars that can be referenced. So to make it clear, what we're doing is we're referencing the true position of the star, and the true position of the star is the calculated theoretical position of the star of where it would be if you had no refraction and then you could just see perfectly 1-to-1 as something's moving away from you. You just never lose that distortion. That would be its position if you just added 15 degrees per hour of motion to it forever. You would just see you would just see it at that position. The apparent position is the position that everyone sees, that in both models, regardless of what you believe in, we see the same apparent position. So all celestial navigation, all models of navigation regarding the stars use the apparent position. All cosmological models, they all use the same apparent positions of the stars, but it's only when you get into cell nav where to use the quote unquote globe, to use the graticule, to use latitude and longitude, which is just snapshots of the positions of the stars on the vernal equinox, so that and then when you know your time, you can figure out where that star would be by adding 15 degrees per hour and doing the local hour transformation and all that jazz. But once we know the angles, we can reference where everything is going to be lined up. So we're referencing the true position. So this red value here, when the true position is lined up with the mountain peak at 231, that's what we're referencing. Oh, sorry, that's represented by this value here. This is for the mountain peak here. Now, the observer on the ground for the globe, they would predict that the star is over here at 204, but that's not necessary. It's not
geometric
necessary.
drop only, right? That's just accounting for the drop over distance for that amount. Is that what you? All right.
Yeah, so I go over both derivations. Like we went over the how they would do it, how some people do it, and then how Mike does it with the full 360 thing. But just focusing on where the true position is of the star with respect to the mountain peak, that's represented by this 231 angle right here. And then the observer right here would see a refracted position of the star. That would be, a lower angle. It would be this 222 angle. That would be their refracted star position. And then if you were on the peak as well, you would see if you were on the ground, you would see the true position of the star would be down here for you. So this is kind of how all that works. And we're looking at the time and when this isn't visible anymore. And we're comparing the true position intersection to that time that it's occluded, because on a globe, there should be no physical relationship to an angle that corresponds to this time, or to a time that corresponds to this angle, because it should be lower, because the star should be allowed to, there shouldn't be any physical mountain there to block it. And occlusions are a physical process. That's something I probably should have covered in the beginning of this. But the basic premise is how we're basically told that that there's unlimited refraction and everything will just always be lifted up at a 1-to-1 ratio. That's not true at all. You can demonstrate the specific ratio of when something it actually physically is intersected by something or by a physical object, and then it's no longer visible. And because we're dealing with point sources of light here, little dots of starlight, it's not the same as like when they say, oh, well, there's a ship and it's being refracted up and, we can see the whole bottom of it or whatever. Like there's not that 1-to-1 translation. It's a little tiny dot. It can't be, 20 plus arc seconds underneath an object while also above it as well. That's preposterous. And then when we get into some of the measurements here, we'll see that that's demonstrably not what happens in reality, because otherwise the timings would correspond to different angles, because the star would have to still be refracted after in other words, there's a threshold or a tolerance of when the star could actually physically be below this for the observer and it not be visible. Okay, so there was a lot of contention in the celestial theodolite about how to derive the globe prediction. So another way that you could derive that 217 number is by doing 360 times the distance over 2 pi r, and that'll get you an angle of 27. If you subtract that from the flat Earth angle, that'll closely predict where the true position of the star is with respect to the mountain peak. If you do half of that 360 value, if you do 180 times the distance over 2 pi r, you'll get the drop to the peak. That'll give you a value of 217. You subtract your 17 from your flat Earth prediction of 231, and that gives you 217. And then we're all back on the same geometric board there. So as we go through the analysis here,
that's the Heffron method, right? That's exactly
Yes.
what the Heffron method does. Just to be clear, that's the first principle put forth. This is how you're supposed to do it. Now, what happened though, to be clear, is that instead of the Globers being like, "Oh, you know what, our position is wrong," they went, "You're not representing our position correctly. Here's 17 other ways where we can calculate geometric Earth curve with varying degrees of specificity." Right. So, and then I think you're going to get to how we handle that. But just to be sure, this is what we put forth originally, and that formula in the corner has many partners, 360 times the distance over 2 pi r. You can do arc length. You can represent it in so many different ways, and they all kind of are equal until the Globers want it to be something else, and then it's not equal. Then that's the wrong formula, etc. But more or less, it's just 7 different ways for people to represent the globe, quote, correctly.
Yeah, we can see a multitude of different ways to derive this and different outcomes based on how it's done. But yeah, geometrically, when you do this, the globe runs into failure at multiple points. And then when I do an extended analysis, giving like maximum benefit of the doubt to the graticule system and using that to even compute the stuff, there's instances of geometric failure and instances where it actually just kind of reveals that based on the refraction analysis that we can get into, they're compensating for their expected drop over distance by an equal amount of celestial refraction, or double or even triple, which is just absurd. Like if you're triple refracting and then you're talking about Earth curve, then that would be like giving the equivalent of that would be when they have a theodolite measurement and they're like, look, it measured a ball, but there's like that tolerance where it fluctuates. They have to throw out certain measurements. Well, if we just gave ourselves like a 3-degree buffer and we were like, you know what, it's measured flat within 3 degrees, they would just go, what's wrong with, like, they would freak out. So we can see all these points of failure here, and we'll go through that in the analysis. And then the last point that I wanted to show was some of the spherical trig for the analysis that I'm continuing on with my spreadsheet. So we're often told that we're not giving the globe enough benefit of the doubt, etc. We're not steel manning it. They want us to use all these different angles. So I was like, okay, bet I'll give you every angle you could ever possibly want, up to and including spherical trig, using the latitude and longitude system to derive an angle relative to the quote unquote center of the ball, and all that. So anyway, that's all what this is essentially, deriving what the distance and elevation would be off of that, so we can get some approximations giving maximum benefit to the coordinate system and see how all of that works. So now we'll get into the spreadsheet here. And anything from the panel so far? Any questions, or want to go over anything, Shane?
Oh, you got your old spreadsheet here.
Yeah, I was too nervous to use the new one because I'm resistant to change at first. I need to spend at least 13 hours with it, dude.
I have the comment in the mainstream, and I'm doing this for some reason on the StreamYard with my difficulties. I can't make the screen bigger than like 2 inches by 4 inches on the big screen with what you're
Shoot.
presenting. So I have my glasses on and my nose is literally 2 to 3 inches from the screen, which is why I'm keeping on my back camera, because it's got to be like a really good look with it there. But yeah, I'm focusing and trying to follow along.
Well, the one
But
tool
yeah.
you're missing is just pick up a jeweler's loop and apply that to the screen. You'll be fine.
Okay, you know what? I have so many
I
jeweler's
knew you
loops
did.
here.
See,
Yeah.
I knew you did.
But yeah, that's about what I need to do. So I feel for all y'all watching this on mobile, because yeah, I hope your eyes are all younger than mine. But yeah, they're really, really good. But you're making me work. You're making me work. Keep.
Nice. All right. So to continue on, now that we know how the trig functions work, we can get a real basic understanding of how the spreadsheet works and what drives it. So going from left to right here, we'll go over what we put in for input variables, what they represent, and then we'll get into the predictive angles, and then we'll go over the some of the mountain peak, and we'll go over the mountain peaks, and we'll go over the analysis to see how everything fared in the end there. So to start us off here, we got the peak name, star name that was occluded or emerged, the time, date, UTC, year name, whoever did the recording. Your latitude and longitude, that'll be relevant for determining distances and all of that with some of the spherical trig stuff we were doing. And then you enter your peak altitude, your observer altitude, and your distance. So keep in mind, if you guys want to participate, and as Stone says, more data is always encouraged. All you need to do is have the ability to record stars at night and be able to distinguish a peak. And it's helpful to have a daytime shot of the peak in case you need to move or relocate and then identify stars that are hitting the ridge of the peak or something like that. So that's always helpful. But all you really need is the ability to record at night and distinguish the peak so you can tell when it's been occluded and what part it was occluded by, and your latitude and longitude coordinates for you, and you need to know what peak you're looking at, so you can use an app like Peak Finder or something like that to easily identify the peaks in your area and the direction that you're looking. And then you can get all that information, plug it in here after the fact, and get your predictions and see where everything lines up. And that's how easy it is to participate. I know there's a lot of flat earthers that have recording equipment and the ability to record stars and such at night. So if you want to participate in that, submit your mountain peak occlusions or emergence. You can do emergences too. Emergences are a little harder because you have to record the whole time and you're just blindly recording. If you're doing occlusions, if you look around a little bit, you can adjust on the peak line and check the ridges and see if you see a star coming in, and then restart your video and then start from there and get a nice fresh occlusion.
Well,
you can kind of hunt them.
I don't know. I think you can tighten up the method a little bit there by just a little bit of preemptive planning. Because you're using something like Stellarium, digital astronomy software, to find out what the angle is at a particular time, then nothing is stopping you from looking in advance. Like you can plan, all right, I'm going to be here between these hours. Let's run Stellarium across that time and see which stars that are bright in the sky and obviously trackable more than their neighbors. And you can put a list down of expected times that things will emerge over the peak as you're looking east, for example. So there's very little guesswork there to be done, actually.
Oh no, you could absolutely do that, but that requires a lot of effort. Some people would just like to go to a peak, shoot, and you could backwards figure it out later. It's the same exact process because it doesn't matter. You can figure it out either way. But yeah, you could do that just to make it simple for people. Though they could submit their stuff and we could find the stars for them, or you could sit through and figure it out and do it that way. But yeah, they're equivalent. Actually, our buddy Goose did that for the star Regulus for the peak that he lives at. He went through and found when it would intersect with it because it's a named star. So he wanted, and it hits right on the peak in his video. He actually pre-planned that one, just doing the exact method that you said, Stone.
Yep, works good. So tell us about AB14 and the rest.
Yes, sir. All right, so to continue on here, we got our intersection angle with respect to the peak. We got the refraction angle with respect to the peak, and we got
some of the characters, the non-alphabetic characters that you're using there, like in A14 at the far left. What do you?
Oh yeah.
To me, that looks like Aries. You know what I mean? What's going on there?
Absolutely. Let me start with the legend first. Good call. So the Aries symbol here means that it was derived from the position of the angle of the star at the time of occlusion. So whatever time we have up here, it's derived from that. And for when we get into comparisons for the different models, we have Gamma Globe, which is mainstream curvature drop over distance. And we have Mu Globe, which is the Heffron method using the 360 times the distance or 180 times the distance. And we have Epsilon Globe.
So what's the difference between those two, between mainstream and Heffron methods of computing curvature? What's the difference?
Yeah, so the difference there is they do the trigonometric function where they turn their expected drop into an angle and then subtract it. Heffron just multiplies the 180 times the distance, over 2 pi r to get the same effect, and then subtracts it from the flat Earth prediction to get it. And then the other thing for gamma globe is a refraction or a terrestrial refraction correction, even though we just went over how it doesn't, like, our methodology eliminates the terrestrial refraction between us and the mountain peak. I just wanted to see for funsies what it would be if we used that angle to calculate the elevation of the mountain and distance back to us, using that to see if it helped their case at all. So the gamma globe also includes that as well. And then we have epsilon globe, which does the inverse of what we're doing, where we're using the true position with respect to the peak. We're using the apparent position with respect to the observer. And then from that, we do the same process of deriving what the drops over distance would be, and what the and then how that's going to affect the elevation, and then how that and then what occlusion timing they would get off, like how the occlusion timing rather compares to what they're able to derive based off of those angle factors that they're locked into.
It seems like a lot, but I remember each time we represented the globe some way, there was a glober who was like, "Nah, do it this way," and we were like, "Okay, here's epsilon, here's mu, here's this new globe method where we do the thing that you just said and how it doesn't help you." Because like, all right, we were like 360 over 180 divided by 2. They're like, "No, you have to use 180." Fine, all right, we'll do it that way. Whichever way, and then that's why there's so many methods now, because the globe couldn't agree over which was correct. Again, keeping in mind the starting Heffron method uses stellarium to confirm the globe predictions, so you're not off in fairy tale land where everyone gets their own prediction with no corroboration whatsoever.
Yeah, that's the thing I like most about this, is we can check the time with the angle with stellarium, and we can see, which ones of these matches and how much they'll affect the measurements. And yeah, on top of that, this started with just a real simple comparison with flat Earth and globe, and I had the ability to adjust the angle to make it anything they wanted. And they were like, "Nope, you have to put in real refraction, the real extra regular way." It was like, guys, it's just
Okay.
about the angle.
Well, I'm seeing a boatload of figures all to compute the same thing using a number of methods. To me, that demands a graph. And I would want, personally, I'm interested in seeing how these relate to each other in terms of total difference of this particular compensation or this particular method to produce curvature. You know what I mean? To calculate the drop using their methods, one method to the next. What is the difference between those values that they are arriving at relative to the total angle? How significant is it that we're using this method or that method? What kind of difference is that producing for them? It's one thing to say that neither work, but it's another thing to say that, well, why would we bother using another method when it's only this different from the method we're actually using, proportional to the total angle that we're computing here? Does that follow?
No, that follows entirely, and that is the exact point of gathering all this and getting it all ready for
Right.
that. The graph stuff will be forthcoming.
Because once you get to that point and establish that it is such a small percentage and an insignificant difference regard choice of method, you can discard the rest and say, look, there's going to be an X% fluctuation of your value, and that's insignificant to the total because of its actual size.
Dude, I like that you see exactly where I'm going with it. That is exactly why I'm doing all of this. And then it'll be, further refined and stuff, like as I learn how to do more stuff. But yeah, that is exactly the point. And there will be graphs to make it, visually understandable as well. But yeah, the figures we're going with in a lot of scenarios, they're like, it's indistinguishable. It can lead to an indistinguishable scenario where neither one is better than the other. So to say that, like, oh, the globe Earth wins here or flat Earth wins here, like, when the margin's that little, it's like, did anyone truly win? But then we have measurements where we can see actual discrepancies, and the discrepancies are always one-sided, where it shows flat Earth is the more accurate prediction. But yeah, so let's see here. Starting with the blue columns here in the E section, we have the flat Earth angles that are predicted off of the values over here that we put in. So we got what we would predict in terms of angle based on the distance and elevation difference between us and the peak, and that gives us an
So
angle
what you're saying is
of
that this is the
231.
flat trig calculation to produce what we're seeing in D4 in degrees, minutes, and seconds at 2 degrees 31 arc minutes, and I guess D3 2.52 degrees. That this is the flat trig calculation that we were looking at in the first frame, and that's how you got there.
Yes, that is exactly it. And then from go ahead.
No, I was all done there, just to clarify how we got to the blue part.
Oh, gotcha. Okay. So here we now compare the, so doing the same kind of trig function to the mountain elevation and the occlusion timing with respect to the true position at the peak, we get these values under the angle that we predicted. So this is our predicted angle, and these are the values that are derived based off of the true position on the peak at the time of occlusion. So with that, we can get a mountain elevation of 2,260. So we're
And
actually,
he landed it. All
yeah,
right.
we actually overshoot the peak a little bit because the occlusion timing corresponded to an angle of 233, and we have a distance here based off of that comes out to be 49,000. Whew, got that one too, Stone. That was a close one.
Kicking ass.
And that's over a distance. Now, remember, our starting distance was 50,000. So we're deriving what those distances and elevations would be based off of the occlusion timing and one other of the known variables to see how close we get. Now, as we go down, we see what the globe does for drop. So to compute their drop over distance, earlier I mentioned the square of the radius squared plus the distance squared minus the radius. That gives us 200 meters for a distance of 50,000 meters or 50 kilometers. And when we convert that into an angle by doing that same kind of trig function that we did earlier to get what it would be for the rise over run, essentially, we get 11 arc minutes. So we subtract that out and we get our 17 there. So there's our 17 value. And then for the terrestrial refraction lads out there that absolutely insist this must be incorporated, here's our terrestrial refraction derived by turning 7/6r into a function of degrees per meter.
So just to cover for the people who've never seen that before, the difference between 2 degrees 17 arc minutes and 2 degrees 19 arc minutes, of course, is 2 arc minutes, 60 arc minutes to the degree. That is 1/30th of a degree in difference between the two.
It's also 2.4 arc seconds per kilometer. That's what it breaks up 7/6r into the ratio. That's how Riff applies it, right? So that's what it comes out to.
Yep. And to note, like the amount is small, but the impact that it has depends on the angle and the distance because it's a ratio of those.
The distance, yeah.
So like in some measurements, it doesn't have much of an impact, but in others it'll have a greater impact. But it still isn't enough for anything to help them in the way that they insist as using this as the physical angle for it because it matches what they would optically have to predict using terrestrial refraction and globularity instead of acknowledging optical compression. So anyway, when we get everything, start deriving our values off of the occlusion timing with respect to the 219 value, we get an elevation of 172, and we get a distance that's 4,000 meters off, 4,200 meters off. And when we do the stellarium timing, so instead of using these refracted timings or raw globe, we do raw globe down here with Mike, with Mike's method. We're just showing that the equivalence here for what they derive every time in every instance is exactly equivalent to what 180 times the distance over 2 pi r predicts. But so moving down here, we have epsilon globe, which actually which is our inverse comparison, which is doing the apparent position with respect to where the observer's at. So using that position, we get a little closer here. We get 125 in terms of distance or elevation for the peak, and we're 3,000 off in our distance. And then continuing on down here, we have the raw values for what the globe predicts. So when we're using their value for 217 for their raw globe, because again, we've eliminated the refraction between us and the mountain. We only care about the celestial occlusion that occurred and what angle that happened to be. So the terrestrial refraction is actually irrelevant. And when that comes out to when we come out to deriving the distances based off of that, we get 202 in difference off there, and for distance we get we're 5,000 meters off. And then
So just for people not paying attention, again, people have just seen this. If we start up above row 30, when you're looking at the difference of 4,200 meters at 20, D20 is where this starts. You see that purple figure, yeah, down one cell from there. Exactly, that is the difference of the two out of the 50 kilometers that we're talking about. We're talking about an 8% difference in computed distance between the observer and the peak in terms of the flat line distance, that 50 kilometer line there. This is how we're coming to 8%. And again, at D27, where it shows a 3,000 or a 3 kilometer difference at D27, that again will be a 6%, down two cells from there. There you go, 6% difference when I'm talking about the 50 kilometer length between you and the base of the peak. So again, for the people who are just seeing this, when Alan said we had the flat trig values in computing in Arc10 at the very first frame, he said once we have these two, we can compute the other one. Well, what we're doing is we're using the angle and the rise to compute the distance in this case, and looking at the discrepancy between the flat trig distance of 50 kilometers and how that would backwards mathematically arrive trigonometrically to this figure with a difference of 6 and 8% depending on the method. Go for it, Alan.
My man. Thank you, sir. All right. So then I then continued the analysis from that with some what do you call it? Spherical trig estimates using the graticule to its fullest extent with latitude and longitude, and then doing the spherical trig based off of the 3959 radius, and then comparing what those come out to be, and those end up being a little closer, especially on the elevation there for that one. But this analysis incorporates like basically really stepping into the graticule, like to get it so it's like self-referencing something that's built on the apparent positions and whatnot. So it's going to have a little more consistency to it. But when we still run into some scenarios where we show the massive difference there, and also when we compare the refraction, how the celestial refraction affects these, what we see is that celestial refraction actually ends up being equal to or double or triple the amount of expected drop over distance for these measurements. And it works out in such a way that the occlusion happens at the raw flat earth angle, but the actual thing is off. And we'll see what that looks like here as we continue on. But what we can do in the same way that we derived through doing the rise over run, we can do how much the angle of refraction affected the drop over distance to give lift. So we can do lift over distance the same way they do drop over distance, and we can compare what goes on there. So that's what we're looking at down here. So remember, they call for 200 meters in drop, or 13 angular arc minutes of drop, but they have a celestial refraction correction of 16 arc minutes angularly, which gives them 240 meters of lift. So that's what we're dealing with there. That's why the occlusion angle for the observer comes out to be 222 versus where instead of
As row 24.
Yes, thank you, sir. Row 24. Yep, there we go. So that's the difference between those and how it impacts the measurement. So we can see the exact amount there. And then at the bottom here, we have the lift difference and clearance. So what that's doing is taking the difference from the true position and the refracted position and seeing how much lower that that true position was relative to the refracted position before it was no longer visible. So we can see the impact of the lift that they're doing there on that. And so we get a difference in clearance essentially. So we can see exactly how much lift is, how much refraction they're refracting, because no amount is too much for these people. So you'll never, just optically looking at something, they'll never be like, oh, it's just what it is. Well, we can see like how reasonable or unreasonable the timing, the angular differences and timing differences based off of when it was actually no longer visible, and set a threshold off of that.
Yeah, there is no distance at which you can make an observation on the ground where they'll be like, oh, you know what? That's too far for refraction. That's never going to happen. So.
Yeah, dude, exactly. And then so like they try to, then like if you're dealing with celestial stuff, well, that's the apparent position of a body. And if you need it to be in a certain position to have a known terrestrial location, well, guess what? You're going to make it fit however you need to and invoke whatever amount of refraction you need to, because that's what it has to be to make your whole thing work. So. All right, so we have a little summary here, and this will be reworked. This is like pretty poorly done, but it just basically takes the values from the distances here, sees which one was closer, and gives us the output here. So in this case, for the oh yeah, we also have it set here. So in the case where the elevation difference is not greater than 60 meters, then it's ruled indistinguishable. And same for the distance. If it's not better than a mile or 1,600 meters, then it was ruled indistinguishable. So for Pikes Peak here, we have an indistinguishable difference in distance when we use the logic's off on that. That's oh, never mind. I'm reading that wrong. That's just the guidelines for it. Sorry. So we have a clear victory here, just using the raw trig values against all their computational models of refraction. So gamma globe, mu globe, and epsilon globe all fail there. And then when we get into the actual Heffron analysis, as Shane mentioned, there's different analyses that are going on. But when we just compare raw trigonometric globe Z over flat Earth prediction, just raw trigonometric, what we see is complete failure of the globe. We're off by 36 meters. They're off by 2,200. And when we get to distance, we're off by 800. They're off by 5,000 meters. All right, and then we have the ratio of refraction influence and the lift over drop here summary. So 240 meters in lift. What's up?
Is it still Pikes Peak?
Yes.
So the expected globe drop 201 meters, and compared to refracted lift 240 meters.
Yeah.
Okay. Yeah. All right. That's hilarious. Okay, I'm just saying.
Oh, dude, just wait, man. It gets worse. So yeah, that's how we're analyzing the data and what we're going through. So now we're gonna breeze through some peaks here, so we can get through this without taking too long. But that is the basic premise of it, and it doesn't get much simpler than that, other than it gets advanced when we get down here with the other computational stuff. But the basic, everything you need to know to understand it is does the raw globe and or flat Earth angle get more closely to the distance or elevation? So we're going to look at another instance here of a different peak. This is Bljette Peak, coming in at an elevation difference of 797 meters, a distance of 35,000 meters. And from that, we get the relevant angles for flat Earth. Comes out to be 116, so 1 degree 16 arc minutes. And then when we have our occlusion timing, so we have we come out to be 51 meters off in elevation and 2,400 meters off in distance. And then the globe, based on their drop over distance there, they predict 100 meters in drop. Sure hope they don't refract it up or double refract it or even triple. But we'll see what happens as we continue. So we have 9 minutes of angular drop that we're going to subtract from the flat Earth prediction. giving us a nice clean 16 arc minutes, or I'm sorry, 6 arc minutes, 1 degree, 6 arc minutes for the raw globe there. And we go ahead and do our triangles there. We get 18 meters off in elevation. We get 4,300 off in distance. And then for the apparent position, we get 163 meters off, and we're 6,000 meters off in distance. And just showing the raw globe there at the bottom, they end up being 101 meters off on elevation and 5,000 off on distance. And so let's see, the refraction lift there was 39 arc minutes. That seems a bit extreme. that's insane. True position minus apparent.
Do you have visuals or anything on or diagrams? I'm a girl. I tend to, when you do math for this long, I forget what you're mathing.
Everything is always going to come back to this essentially.
This, right?
It's
So-
always going to be some variation of, we know this angle and we know one of these two values, and we're going to derive what it would have to be based off of one of these inputs, or one of these two inputs.
So a lot of the math that you're seeing there, Cami, has to do
Yes.
with the green line. Is it a straight green line or is it a curvy green line? Because the 2227 actually doesn't really change regardless of scenario because of altitude. Altitude just is what it is, and as you move, vertical becomes a moving vertical reference. So we're looking at how the curvature of the green line might affect the angle of the purple line against it from the observer point, and how many differences we're going to get between the observer point and the peak and the observer point and the star, and the things that happen between the star and the peak, and the things that happen between the peak and the observer. And that there are ratios of compensation there that the globies are insisting on. And what we're really looking at here by plotting them all out side by side is just how significant are those compensations. Now, the difference between in terms of significant figure between Pikes, which we looked at first, and Bljette, which we're looking at now, is that the angle, the purple angle for Pikes was about 2.5 degrees, as you can see here, but Bljette is only about 1.25. And when I looked at all 7 or 15 different tabs worth of observations that have been plotted so far, the first thing that occurred to me, which I walked Alan through, was a graph to produce the plot of the angle. What is that? Is it 1.25, or is it 2.5? Or in another case, it's actually 10 degrees in one anomalous case. And some of them are much even closer to the horizon. For me, what I found interesting was the relationship between that degree, that angle, and how much of a discrepancy between flat Earth trig and globe Earth exists in the end product figure. Right? And that actually produces a fairly logarithmic curve as you approach zero angle. We see a lot more discrepancy between globe Earth trig and flat Earth trig. That when things are a really large angle and you're looking far more up into the sky, the points almost congrue. And maybe we'll get to those down the road. But that's what you're seeing in these figures.
Okay,
Yep.
and I do think it's important that we pull away from the figures like more often than we are, just to like reiterate and stop at that, because
To simplify and summarize. No, I can.
yes.
I feel
Yep.
you. I feel
Absolutely.
you. Yeah.
Absolutely. All right. All right. So let's see here. We went over Bljette here. We got our stats.
Where is Bljette, by the way?
Colorado.
I know Pikes. It is. Okay, I'm
Yeah,
a Colorado girl. I know
that's another
Pikes Peak.
Heffron
I was
location.
just trying to find it, but okay.
Heffron had about half a dozen different peaks that he could see from his backyard, all looking essentially to the west and slightly north of west.
Yep. And all right, so we look at the refraction corrections here. So remember, they had a nice clean 100 meters in drop. Seems pretty innocuous. Oh, wait a minute. Are they lifting it up 400 meters? Ah, shoot. That sucks. So now we have which one is that one? Is it this one? Yes. So this now is our angular discrepancy between true position and refracted position. And this is where I was talking about that angle of intersection where when the star is it can only be like this low before it's actually not visible for the observer over here. But they're saying like, nah, it's definitely down here, but still up here is what like. That's the discrepancy that they're invoking. So it's in other words, this is just whatever it has to be for this to still be on a globe.
It's geometrically way down there, but apparently refracted way the hell up there. I got it. That makes total sense on a globe, dude.
Yep, because when we get to the intersections that quote unquote prove the globe or prove that this method doesn't work, we'll see that the angular discrepancy is much smaller based on the occlusion timing, showing that like it gets unreasonable to have that. Like this is a curve fit, as they say in the business of plotting things with a coefficient that gives you exactly what you expect based off of what you need versus what there is. And yeah, so when there's a negative difference in clearance, like that's really bad because the star shouldn't be visible, and it is for them. So, all right.
Wait, all those globe methods and they all fail? Is that what you're saying? All those colors, all those Greek letter designations for the different ways to calculate, and none of them worked?
All those globes and none of them helped. None of them helped.
Damn.
Yeah. Yep. So yeah, if you go off of the raw, or if you go off of the globe refracted and all of that, you get indistinguishable. But if you go off of the raw globe versus raw flat, there's a clear distinctive winner there, and the globe is off by it's not on that comparison there, but
So to say it-
1300.
So to say it another way, when you
No,
allow
13,000.
when you allow the internal consistent model to use coefficients that are internally consistent, then that would work. If you take one external reference, say an actual occlusion time, then the whole system breaks and it's flat every time.
100%. That's such a great point, because when you like I have the summary split into internal consistency check versus external consistency check, because the refracted position check and the way that they would like to do it requires you to basically tell Stellarium your location first, to tell your distance, so when you backwards derive things based off of that, using a system that's designed to do that, well, it should give results that correspond to that. But when you do the external check for the raw positions with respect to where it would be physically, where it would have to be, they're off every time, except for I think one scenario that we'll go over where it's where there's a mix match, where if there's a mix match, then if both of these aren't definitive winners, then I declare it a mix match.
One point here in the nomenclature that you're using, Alan, I think I've been watching it get you guys into a lot of argumentative trouble with the globies, and that is the expression to backwards derive. I think that's a total misnomer here. Okay.
Yeah, I agree.
Yes, it is, and it's my fault. I apologize.
Let me get the rope and hand it down to you guys, and we'll pull you out of the well. Okay, because all you're actually doing is flipping the variables around and solving for the other. Like I was describing, when it comes to when you know the green line variable and you know the blue line variable and you're computing for the purple one, okay, you got that and you got the time. Okay, now what you're doing is you're flipping those variables around to find out what the green variable is dictated as being when you use the other two as fixed values.
Yeah, I guess intended trig. So it's just
all we're doing here is we're just flipping the variable. Nothing about the observation is changing. That's key to point that out. It'll save you guys a lot of argument in the future.
Yes, and I do often, for some reason, just say backwards derive. So it's
you're seriously just making it so hard on yourself by doing that. You're opening the door for the globies to just throw in a bunch of controversy and convolution and conjecture when none of it is appropriate. you know?
Absolutely. And thank you for reining it in. Hopefully I stop doing that. Or
Train
at
left
least,
the station,
or
but we can hope and pray or
well,
whatever.
well, when I do it now, I like make a point to correct myself. I'm like, I often say backwards derive. I just mean calculating it. They're all the same. There's nothing
You're just
backwards.
flipping the variables in the algebra. That's
Yep.
all you're doing.
Yep. Okay. So Mount Rosa now, we have an elevation of where's my elevation? An elevation difference of 1,400 meters. We have a distance of 47,000 meters, and we have our occlusion angle here of 42 or 1 degree 42 arc minutes. Now for our flat Earth prediction, based off of these values here, distance and difference in elevation, we get 1 degree 43 arc minutes. And based off of the occlusion timing, we derive a distance and an elevation that is 7 meters off and a distance that's 232 meters off. When we do the globe drop, we get 178 meters, comes out to an angular drop of, what is that, 12 arc minutes. When we subtract that 12 from our 143 from our flat Earth prediction, we get 130 for our raw globe. So our raw trigonometric globe is 130 there. And then,
So back up just for a sec. For significant fig, everybody paying attention. That's D6. That's 6.96. That's 1/2 of 1% off of the figure. Continue.
Yep. All right, and then we have let's see here. So distance as well. So our distance was 232. They're 5,000 off on their refracted, idealized terrestrial refracted angle, and then off their celestial refracted angle down here at Epsilon globe, they're off by 87 meters on the elevation, and they're off by 3,000 on the distance. And then when we continue down here for the raw globe, we get 171 off of the distance or elevation, sorry, and 6,000 off of the distance. And then for the other computational purposes, gets pretty close down here for elevation. And then for distance, they're 2,500 off.
So we're looking at 8 to 10% as opposed to 1/2 of 1%, method to method, scenario to scenario.
Mm-hmm.
Well, scenario to 7 scenarios to be specific.
Scenario.
Well, yeah, flat
Yeah.
to whatever they got. Yeah.
Yes. And then so like so down here we got the refraction here. So we have 5 degrees of lift here, 5 arc minutes of lift. So we have 270 in lift, and their refraction or their drop was supposed to be 178. So like we see the pattern here now. It'll either be equal to or like 1.5x or 2x the amount expected.
A proportionate ratio of drop to refraction. No way. Who would have thunk it?
Yep. Yeah, we'll and then we'll see how important that is in these later measurements when the flat Earth prediction appears to be off, but then the occlusion angle equals the raw flat Earth angle. Like it gets preposterous out there. So we'll see, or we'll see what happens. I mean, the refracted position equals our raw trig angle, so it gets precarious for them because it shows our method is true with the occlusions. Anyway, Greenhorn here, or nope, this says Blue Mountain. It's supposed to say Greenhorn though. That's it's gonna bug me 1 second. Green Mountain. All right, we got Green Mountain here. We have all the relevant values here, giving us a distance of 52,000 meters and an elevation difference of 1,000 meters. This is going to give us an angle of 1.6 degrees. And then for the globe drop, they predict 217 in drop over meters. And then they have converting that to an angle, comes out to be 14 arc minutes. Subtracted from the raw flat Earth, we get 51 arc minutes. And then their refraction here is 23 arc minutes. So they predict angular drop of 14 arc minutes. They're going to go ahead and hit us with a 23 arc minute refracting off the dome. All right. So then when we go through and derive everything, we get 185 for elevation difference. Oh, I'm sorry. Starting with flat Earth, we're 17 meters off in elevation and about 1,000 off in distance. They're 185 off off in elevation, 11,000 off in distance. Apparent position, they're off by 86 in elevation and about 5,000 in meters. Raw globe to raw to true is 218 meters off and 14,000 meters off in distance. And graticule tricked out spherical globe is 129 off in elevation and 5,000 off in distances. And then we look at the refraction here. Oh, they lifted it up by 366 meters. Expected 217 drop.
So scroll all the way up and take a look. Just to recap here, that we're looking at the angle, the purple from the first frame here would only be 1.1 degrees instead of 2.5. And this is why the differences between flat and globe are much larger. That the observation itself, the angle is being done at closer to the horizon, as in closer to zero. So the discrepancy between the two is larger proportionally.
That's also right with the refraction, the celestial refraction equation that we're using has the highest discrepancy if you follow that curve right at the horizons where it's the biggest effect. So just saying, things to note, right?
Yep. All right, so that's our summary there. So we get what is that? We get 28 arc minutes in difference there between the positions. Like that's, or no, wait, that's not the right one. It's that one. This one. Four arc minutes in separation here. So over the 4 arc minutes in separation, they created double, like essentially double the amount of drop. That's very cool. And then moving on to North Peak. Sorry, did you guys hear that, or was my mic muted?
People get confused with your deadpan delivery of "that's very cool" for the globe nonsense that they just pulled up, like sarcasm notwithstanding.
Yeah, sorry about that. So here's another cool measurement for the globe. Is that better? We have North Peak here. Now this is our greatest distance here. So we have 130,000 meters, and we have the elevation difference of 1,600 meters. So for our angle here for flat Earth, we predict less than half a degree.
3/4 of a degree.
Yeah, a little less than half a degree.
No, it's
So-
3/4 of a degree.
Oh yeah, 'cause it's yeah, you're right. 45 arc minutes. So, sub 1 degree in elevation here. So we're going to see how that affects the measurement. So we have, based off of the occlusion timing that happened here at 1 degree, or yeah, 58 arc minutes. So almost 1 degree. We get an elevation of 516 meters, and in distance we're off by 30,000 meters. Well, that seems like a lot, but we'll see how the globe fares. So 1,300 meters in drop over that distance, and that comes out to be 35 arc minutes subtracted from our raw value there. So they predict the raw globe being 9 arc minutes there in angle.
What?
Yeah.
Versus a half. Wait, what? What was the flat Earth prediction?
45.
Okay. All right.
Yeah, this is the smallest one furthest distance ever done. And then it gets real precarious because they predict the true position to be like under the horizon. It's crazy. Okay, so continuing on here, based off of the occlusion timing of 58 arc minutes, we get these values here. We get 5,500 meters in elevation, and we're off in distance by 270,000. That sucks. And that's using their terrestrial refracted 14 arc minute angle, using the actual measured celestial refraction 18 arc minute angle. They get these values: 684 meters in elevation, and they're off by 192,000 meters. And then we have For the raw globe there, they're off by 500,000 meters. Unlucky.
That seems like a lot.
Yeah, it's quite the discrepancy.
I almost on these numbers and everything because it's just, and this is, I know we are talking to the spreadsheet kings and the mathematical whizzes and our calculus kings, whatever, algebraic geniuses and all of that. But when you are talking to the audience and putting out on the sheets like this, you're making the point, but we're not like, when I say we're not, I'm checking in with some people I'm talking to on there. I'm a very, very visual person who can sit and do math. But when you say the math, I'm not seeing the picture.
Okay.
You almost have to keep on going back to the picture each time, say this line is going up, they're seeing it higher, we're seeing it lower, they're seeing it further apart. Because I think that you're probably doing very, very, genius proofs on here.
I think also
And
too, like, yeah, if you had a graph like this that also had like a right alongside of it, like the same measurement with one of the globe Earth calculations, so you could visually see the difference. Kind of, I mean, I guess it's kind of similar to the graph idea, but I think even for more people to get a grasp of it, it would be good to have maybe one right next to the other. Does that make sense?
Yeah,
you're going
absolutely.
to,
So
and
Cami, check
this, yeah,
if
go ahead.
if you check this out, I'll try and give you like a live walkthrough of
Mhm.
what we just witnessed there.
Let me put my glasses on it. And please, thank you.
No worries. So I just
I feel
changed.
silly and stupid, but I'm going to
No,
put it out there just because I
no,
usually learn pretty quickly, and I can't seem to. You're going from one thing to the other. It's like that's kind of a long distance, that's short, that's that, but I'm not touching, and I
yeah,
know that each one is significant.
yeah, no worries. We'll get right through it. Do it. So what does the globe predict? They predict, or they got 218 there, so we'll do 218 or 18 and same scenario. Okay.
You have the interactive graphics that can already work for me.
Kinda. Okay, so for the flat Earth prediction, based off of the values for this peak here, we get this relationship. This is what we're predicting for like the raw values, and then based off of the time that it was actually that sorry, based off of the time that the star was actually occluded, or the the angle that we get out of that, we get 58 arc minutes there. So instead of having 45, we get 58. So so now we derive the distance based off of the angle now, instead of uh, instead of already knowing it, because we know the elevation, we know the distance. So now we can say, okay, what would the distance be when we do this relationship now, instead of doing these relationships to get an angle, because now we have an angle and we have an elevation. Well, what would the distance be? So when we do that, it comes out to be 100,000. So it's the value that we need to get is 130,000, but using that timing and angle, or you're using that angle, we get 100,000. So we're off by 30,000. Okay. Does that make sense so far?
Okay.
All right. Now we can do the same relationship too for this elevation of the peak by using the known distance and the occlusion angle. So what would the peak elevation have to be? So when we do that, we get an elevation of 22. Yeah, we get this value here, 2,208, 2,208. So that becomes this value, and we have to compare it to that previous value there and see how much they're off. And whoever's the closest, but that geometry best represents the ground. Does that make sense?
Theoretically. And when I say
Awesome.
theoretically,
Yeah.
I'll say that like when, in my personal opinion, just working with the different optics and that, because when we're looking at the stars, and again, you're looking at where your perspective pulls into it, but more than that, you're looking through a known magnetic field. You're looking through a known something even called the heliospheric current sheet. That's an electric current that's floating. I mean, different known properties that are floating all above us. That we're put in other words, I understand trigonometry measuring and doing this on known distances, but I think the second that you're putting them in the sky with possible crystalline boundaries, known magnetic boundaries, known electrical boundaries, and all kinds of things that we know are going to mess up your optics, for us to say that's where they are, that's kind of like triangulating to a fish when you're doing spear fishing, and we all know
Oh,
how well that would
yeah.
work.
Yeah,
So I mean,
luckily we're not. Luckily, none of that
you were
matters because we
right.
only
'Cause
care when the star is not visible. So when it's not visible,
Mhm,
none of the
mhm.
heliocentric current sheets matter. So
How would it
that's
not? Right. In
that's
other words, these are okay.
yeah. So we
I'm
just
saying
we just
in
care about the angle
both
that we
models.
don't. Yeah, we
Yeah.
just when we don't see it, that time corresponds to an angle, and then we do trig based off of that to see if we can derive our distance and elevation.
Yeah, no one's measuring the angle by looking at it. That's not part of it.
Mhm. But the globe is deriving the shape by it.
Not for this method, but that's why there's 7
Okay.
globe methods.
Yeah.
Yeah, there should be a clock here.
The Heffron method uses the true occlusion time as the actual, reference point. So there's no actual observation of an angle from anywhere besides the mountain. You're only at the mountain. That's the whole point of the process. And when you're at the mountain, that time is an angle.
There we go. Time equals angle equals 58. And then we derive everything based off of that, and we see who's closer. And then so when we do the globe variant of that, they have they always predict a smaller number. So when we ratio that out against the other known variable, their distances are always going to be skewed. When we derive the elevation based off of the distance because of their smaller angle, their elevation is always going to be smaller. They're always going to end up with a tinier triangle. Their distance isn't gonna quite represent it there.
Smaller angle equals smaller triangle, right? That's the whole point.
Yep. And then so continuing on here, we got does that relationship, does that help now?
This is helping a lot. Thank you.
Nice. Awesome. Okay. Yeah. Anytime you need to go back to it, just let me know and we'll plug it in, because it was hard for me to to fully grasp it. The only reason I got it stuck in my head so far is because I've been looking at this spreadsheet for the last week, all week, every day. I see in spreadsheets now. So, so when we go through the spherical trig stuff they're a little closer in elevation to what the compared to what the other stuff, how bad they were off. Like they're still off, right? But they're oh no, actually they're closer in elevation. I misspoke there. But again, that's referencing the internal stuff of like what it would exactly be. And then but for distances, they're shredded, not even close. Like 260,000 meters off, and then what was that one?
How do they deal with
Just
that?
over
Do they just not
100%.
discuss it, or
Just
Well-
over a clean hundy.
How do they deal with it? Oh, they put up their hands in defeat and they said that we won, and then it was over.
Yeah. So
I wish that's what happened.
So specifically, how the globularists that we're dealing with argue it is they confine the analysis to the angle. And sometimes when the angle is closer to what the globe predicts optically, they're like, look, my globe, I found it. And they ignore the other part of the analysis, which is deriving your elevation and deriving your distance and seeing which one closely matches. Because in cases where the refraction angle equals the same amount, or that would put the position of the star at the same position as the true position with respect to the peak, you get ambiguity there where either one could be true. And so to eliminate optical ambiguity, you derive everything backwards, or you derive everything forwards, and to see which one actually gives meaningful results relative to the angle, because it's all going to change based off of the distance, because it's all a ratio. So every measurement's going to have a unique change in distance that corresponds to it when you derive your variables based off of the occlusion timing.
Karen, do you have any questions?
Not at the moment.
Okay. Alrighty, we got celestial refraction here. So we're going to check and see how much that ended up impacting the measurement. That's going to come out to be a nice clean 40 arc minute difference there, which is, disgusting. We've seen occlusions happen at 5 arc seconds in difference. We've seen it at 10, 18, and now 40 arc seconds in angular difference, which gives them a lift of 14 or 1100 meters. And then remember, their expected drop was 1300. And this is a scenario where they actually predict that the star is 12 arc minutes below the actual globe, not even below the peak of the mountain, but actually below the geometric globe. So they're off in reality by 200 meters in lift there. So this is like a complete geometric failure. There's no reason the star should still be visible and occluded there at this time for the globe, if Earth be globe. That's why these distances are so skewed, because it's just like, it cannot compute, as they say.
So what is the difference between the red one where you say it's stellarium, and then when you go into the middle at the very bottom, it says something about stellarium? Is it two different?
Yes. So the Heffron method comes with like a couple of separate predictions that I haven't plotted yet, and it's not like relevant for the analysis for this. This is just like a separate thing. But yeah, so the 360 one, when you do the full geometric completion of that, it looks like it would predict where the true position of the star would be with respect to the observer. So if you do 180 times the distance to the peak, you would get the position of what they would predict for drop over distance. And then if you do 360 times the distance, you would predict what the drop would be to the star. So it's an interesting relationship there that I'm kind of plotting out. And then where it mentions the stellarium differences, those are comparing where the stars, how far off it was essentially with the true position there. But like none of those are relevant for deriving distances or anything. All of that is done from these two right here. These are the 180 times the distance values right here.
I am, while you're all being complicated, is I'm with Lilihan on here, that before I connected with the flat Earth community, I thought it was so odd, all the frantic motions, the spin, the orbit around the sun, the Milky Way, and the great attractor, and that I'm with her on that. I'm more simplified than you guys. I'm liking where you're going, but I am more simplified, and it drove me crazy about how can we be doing all of these directions. That was just out of the chat. You guys are just taking it to new levels on this. So
we're just meeting the globers where they want to be, right? They can never be wrong. So every time they're not wrong, but wrong, they have a new process. So here's all of the processes that have thus been put forth, because they're still wrong. And that's the whole point, right? But I've never seen a glober go, oh, you know what? You're right. I've never heard that. I've never heard that once in all the years I've been doing this. So I don't know.
Who was it last Celtheo update? There was a guy that was like, now listen, if you guys were right, wouldn't the globers agree? I'm not hearing you.
His main objection was the people are still disagreeing, so you can't be right. I was like, whoa, your worldview could use some improvement. Let me help you out for a second. They will never
has that guy ever looked up the definition of the word zealot?
But it's funny to track this started out so simply, Cami. It was like I had illustrations from like 2 sessions ago. That's just simply we had to add all this stuff because instead of being wrong, they complicated it. Well, you're not doing geometric right. You're not doing you're doing celestial instead of terrestrial. Okay, we'll add terrestrial and celestial. You're not accounting properly for this. It's like, oh, yeah. And now they're like, oh, actually, your flat Earth predictions need refraction in it. What? No. Refraction is the coefficient of 7/6R. Why would we incorporate the radius of spherical Earth into flat Earth predictions? First of all, it's like, it's crazy. And no matter what we do, we're not right, but they're still not wrong. So it's crazy.
This is great. Actually, that's hysterical. That's good to know too, that you started with it a little bit less simple and how you got to the level of it. That's good to know. I mean, I think it's fun if you're all that geeky all by yourself, but that gives inspiration. So
well, globies aren't generally used to analyzing anything that isn't overly formulaic complex. You know what I mean? It's got to be thick in figure, or it's just not valid.
Math is reality, after all.
Yep. All right. So we've seen the massive geometric failure here on the globe for this star in particular. And then this peak had 3 other stars that hit it. So I just added all 3. Added all 3 of those. But we don't have to go over the statistics or whatever because they're all pretty much the exact same. The difference there doesn't change much, but we just see the repeat there of, they expect we're 1300 in drop. They have 1100 in lift. They actually predict it's below the globe, yet it's still visible, and they're off by 200 meters in lift. So there's no actual physical like beyond this negative number here. They're out of explanations right here. They've hit their actual limit for refraction. Guys, we found the limit. We had to go to 130 kilometers and a quarter of a degree off of the ground to find it. But we did it, boys. We found it. All right. So same thing here. Three separate. Excuse me, 1 second. 3 separate measurements, all corresponding to the same thing. Globe's drastically off. Yeah, same story. We've been looking at there the whole time. So even on the regular refractive comparison analysis, they're drastically off. On the raw analysis, for the external consistency check, they're, they got checked there. All right, so now we move on to Green Mountain, or Getaway Mountain, sorry. So this mountain here was done by Catalan. Shout out to Catalan. And we have an elevation difference of 752 meters, and we have a distance of 48,000 meters. And what that comes out to for the trig values is 53 arc minutes, so almost a degree. 1 second. And the values we get off of that are 100 meters in elevation difference from what the known value is, and 7,000 meters off in distance. When we get to the for what the globe predicts and drop over the distance here, 200 meters and drop essentially 188. Converting that to an angle, we get 13. Subtracting from the flat Earth 53 angle, we get a raw 39. With terrestrial refract, we get 41. So we'll take a look at how that fared later. And then we have the celestial refracted position coming in at 45 arc minutes. Now you'll see here that the the peak here. So the true position of occlusion time was 45 arc minutes, and their celestial refraction position. So at the peak, right? Check this out. At the peak, the true position of the star was clocked at 45 arc minutes. For the observer, the celestial refracted position is 45 arc minutes. What do you guys think is going to happen here? For the refracted position analysis, is the globe going to win, guys? Because this is how it was this is how it's been argued. This is a win for them. And it's this is the limit of the instrument. If there's no distinguishing difference between the two, how could there be, how could you falsify one or the other, right? So anyway, continuing on here, we get 160 for elevation with the refracted, and they're off by 1,300 or 13,000 in elevation. Sorry, distance. For refracted globe, yeah, go ahead.
Just saying, no, that's 13 kilometers out of the total of how many kilometers away is this site? 49.
Yeah.
So 13 out of 49, so that's 26% difference. And this is what I was citing at the beginning, and I think you would definitely want to graph this again, and in an even better way than I did for you to begin with. That there's a relationship here between the purple angle, how close that is to zero, and the discrepancies between flatter trig and globe and spherical trig. That because it's fairly far away at 49 kilometers, but it's very low at under a degree off of zero, that the discrepancies between the two methods is very large.
Mm-hmm. Yep. And as we go on, we have the celestial position here at 111 meter or 110 meters and 8,000 meters off in distance there. But remember, the position wise, they're almost identical there. So following the raw globe, though, we get a value. We get 188 in elevation, 16,000 off in distance, and then using the spherical trig stuff, we get 84 in elevation and 4,000 off in distance, and what's the other one? 111,000 off. No, that's a that can't. Oh wait, that's a nope. That's some weird mistake, I think. We'll come back to that. But anyway, going down here, now we have 77 meters, and then off by 3,800 on their internal, like on their merging of the references there analysis. But so for the lift here, we have it comes out to be a lift of 370 meters in lift. So their drop prediction was 188. They lifted it up a nice clean almost 400 meters, guys. And remember, the sky moves at 30 meters a second terrestrially. You could look at it that way. That's the way that's why I have the thing set the way I do for the differences. So if like that's crazy. Like that's almost 400 meters in lift. That's crazy. So there's an angular discrepancy there of 26 meters to get that star at that position over 45. So like what Stone was talking about there.
I wonder if any of them actually analyzed what the physical implications of the things they were claiming are. Like if you actually graph them out and look at them like you're doing right now, like, oh, you're claiming 400 meters of lift and 700 meters of drop. Like, I don't think they think it through that. They just think, well, what does it need to be for my globe to still be real? Like, oh, it's this number. That's all it is.
Precisely. They adhere to the formulate and adopt that as their proof without ever invoking significant figure and looking at the truth. And here we are.
Yeah. And so get this. So remember how we were dealing with these grandiose ideas of like unlimited refraction. Well, we have the occlusion happening at 26 arc seconds between the peak and refracted position intersecting with the true position of the peak at 545 arc minutes. So like this idea of like, oh yeah, it could be like, 20 arc minutes, 10 arc minutes below the thing. No. Otherwise we would have a completely different occlusion angle off of that, if that were the case. So now we move on to, that was Getaway Mountain, right? That we just did? Yes. So this needs renamed Houndstooth. All right, so now we got Houndstooth here. This was the shortest one that's ever been done, and the largest angle, I think. So we have 8,000 meters in difference, so it comes out to like 5.4 miles. And then for the difference in elevation, 1,600 meters, and the celestial refraction amount here is 5 arc minutes. Our occlusion time gives us an angle for the position at the peak of 10 degrees, 37 arc minutes. And the refracted occlusion time is 10 degrees, 37 arc minutes. So it'll be interesting to see what happens here. Predicted drop here, or predicted angle here, 10 degrees, 39 arc minutes. The drop, or the elevation that we derive from that, is 1650. So pretty much exactly what the what that value was over here, 1656. And then for the globe, they expect 6 meters in drop. I sure hope they don't double refract it or something crazy. That'd be nuts. 6 meters in drop. Converted that to an angle, subtracting it from the flat earth and all that, comes out to be 222 for their, or no, I'm sorry, 10 degrees, 36 arc minutes. And then from that, we have the measurement deriving almost 6 meters. So they're, indistinguishable there. The distance, they're off by 28. We're off by 29. And then when we get into the refracted position, same scenario, they're very close, 4 meters in elevation, 525 in distance difference. When we look at the raw trig difference, pretty much the exact same, 6 meter difference, 33 distance. When we do the spherical trig, we get about the same scenario. When we look at how much they're lifting up by 13 meters. No, they doubled their expected drop. Son of a gun, dude.
It's like a reoccurring theme.
Dude, it's always equal or double or even triple in some
Well, I
scenarios.
think what we're seeing here is previously refraction has always been a post-diction where they can retroactively, given the known criteria of your observation, know exactly what my coefficient should be of K to make it so that it doesn't make any sense and that I can bring it right back up. But this makes them predict with it ahead of time, like given the known distance and basic parameters. When you use it to predict, it's never right. That's why it's only an ad hoc post-diction where they can fix it afterwards. But when you're using it like this, not enough, and it's wrong. I think that's an important distinction.
Super important distinction, and that's why we go through and derive it all the possible ways to see it from every possible angle, so that like if globularity does exist, we will find it in the timings based off of the angle.
Been a band-aid of unfalsifiability up till now, right? Refraction. You can just invoke it whenever, it fixes everything, no matter what.
Right.
Right.
And when we see the occlusion difference here between the true position at the peak and the refracted position at the observer, 19 arcsecond difference in intersection. So the physical occlusion happened at this mountain peak with, that is what it is. So now these measurements are brought to us by our local globularist proponent resident named Jesse, who went to try to get some measurements to find that globularity. And we're going to see how that turned out. So at an elevation difference of 600 meters in a distance of 22,000 meters, we get a flat earth angle of 1 degree 34 arc minutes. And based off of the occlusion timing, we derive a distance of 158 meters and a distance of 7,797 meters. For the refracted globe, or going off of what the globe predicts for drop over this distance to that elevation, to that distance, we get 38 meters, sorry. Converting that to an angle here, we get 5 arc minutes. We subtract that 5 arc minutes from our flat earth prediction. We get the smaller triangle of 1 degree 28 arc minutes, different from our 134 flat earth prediction. And so based off of the occlusion timing there, which for us, we're using the 109 or 1 degree 9 arc minute time, they would be using their apparent refracted position, which is 130. Oh, no way. So the refracted position is equal to the raw flat earth trig prediction. Wonder how that's going to affect the measurements. So as we continue on here, they get their distance they get their elevation here of 32 meters in difference, and then 1,200 in distance. Using the refracted apparent position, we get 26 meters and 1,000 in difference, and then using the raw values, 38 and 1,400 again, and then using the old graticule there and some spherical trig, we get 10 meters off and 380 off in distance. But when we look at the refraction here, we have 131 meters in refraction. So the drop was 38 meters. The lift was 131. Stone, I can't remember how ratios work, but what is it when it's triple the amount of the expected?
We use a word like ridiculoso.
And so the difference in position here for the occlusion to intersection is 20 arc minutes to bring it up to the raw flat earth prediction. The
Do you
idea
have
the
a
idea that
refraction
this,
percentage somewhere, like 300% refraction? Did you have that as a metric pull out somewhere?
it's not accurate or whatever. Like I don't have
Oh,
it. It's,
okay,
so I haven't
there
been
it is, yeah.
referencing it. Yeah. So anyway, that's insane. So like the idea that this proves the globe is preposterous. The occlusion timing angle matches what the flat Earth predicts for our raw flat Earth angle.
No corrections, no after the fact post-dictions, none of that required.
Yeah, like our true position angle doesn't match up to it, but their triple refracted position that they're referencing gives them the elevation of the mountain and distance, like within that margin there. So when we look at that over here, we come to an indistinguishable draw for the analysis using the refracted positions. Because remember, the whole purpose of a hypothesis, null hypothesis, is you assume one thing to be true, and then you're going to falsify the other thing. So if we assume that the globe is true for our hypothesis, and then for our null hypothesis, we say the Earth is flat. Well, we have to find evidence to falsify that. So we have to find evidence that there's a measurement that flat Earth can't produce that would be mutually exclusive. These differences produced by this measurement using the refracted positions are not mutually exclusive. They end in a draw. They end in indistinguishable amounts in difference there. And when you go to the raw geometric positions, though, there is a decisive winner. The globe is off by 1400, and we're closer. Or no, I'm sorry. They are. It's no.
Let me say that one says winner GE. How's that work?
Yep. This is this is the mix match one. Sorry, I think you caught it at the same time I did. So over here, remember I said the parameters for a decisive victor, so that it falls within the limits of use of this instrument, right? Because every tool has an instrument. You can't use it unlimitedly and outside of its parameters where it's not going to be able to make a distinction, etc. So anyway, for elevation here, we have a clear distinction, a clear victor. But for the distance derived, like you said, the globe Earth is closer in their distance based on that ratio, and we're off further in that, but that creates a mix match. So the application of this instrument, or the application of this measurement to decipher what the shape of the Earth is, to overthrow our, to falsify our null hypothesis, just, it's not there. It went to a place with triple the refraction. Rating
To
a
be clear,
20.
it's a tiny little hill, and it's not very far
What's
away.
observer altitude at this one?
6
Raw
meters.
observer altitude. So he's right off the water.
Yeah. Observer
Go
altitude
figure.
43.
He went to literally where the refraction for regular terrestrial and celestial would be
Is
maximum.
at a maximum.
Maximum.
Absolutely.
Where can I get it the highest? Is it
Go
about a 1 degree
figure.
right above the horizon at sea level? Let me go there. And then he's like, boom, gotcha.
So compare that to Heffron's observer altitude.
And yeah, and keep in mind too, the raw flat Earth prediction, 134, half a degree. We're basing it off of true position there, but the actual occlusion intersected at 1/3, like at the half a degree. So like literally deriving the distances and everything based off of what we would predict, they get close to what the globe predicts off of their refracted angle. It's a precarious situation. So like they don't win in the way that they think they do because it's, indistinguishable. And then they also doubly don't win because our raw angle equals what they're using as their apparent thing to get closer than what we did based off of the true position. So it's, anyway, that goes on for 3 separate measurements. So I plotted those out. These are all the exact same, showing the same relationship. One of the distances changes. So instead of being 22,000 meters away, this one's 40,000 meters away. Oops, nope, sorry. This one's 40,000 meters away, 6 meters off in observer elevation, and the peak altitude is 635. So really small difference there in delta mountain elevation. But we get the angle here, 53 arc minutes. The globe predicts 41, 43 with refraction. The actual measurement came out to be 42. And in this instance, we're referencing 138 for our Intersection point, the globe is referencing 42 arc minutes. And when we get into what those derive distance and elevation wise for flat Earth, we have 172 for elevation, 15,000 in distance, 500. What was it? 1,100 or 111 for elevation for a globe, refracted 8,000 in meters for distance, 121 in elevation for the refracted celestial position, and 9,000 in distance. And then down here we have similar relationship. They're pretty much spot on with the spherical trig stuff referencing the actual graticule and the refracted position. But we look here and we see that refraction has lifted us 313 meters, and their expected drop was 131. So again, we have this scenario where they're overcompensating by 182 meters and then trying to claim that raw angle, which is closer to what we would predict, gives them their measurement. But that's why we get this scenario here again, where there's a mix match in this scenario where there's a triple refraction amount. It doesn't lead to something that falsifies the null hypothesis. So if we're globers and we're null hypothesizing and we're trying to falsify the position that the Earth is flat, we're running out of measurements, guys. There's only one more to check and see if there's a globe here. So we'll breeze through this one real quick because I'm sure we're tired of hearing numbers rattled off, and then we'll do a recap on the significance of what we saw with some visuals. So for this instance, this was done by our boy Goose. Shout out to Goosey. And we have the elevation of 1,400 meters in difference. This was done where the observer is 4 meters above sea level as well, and a distance of 16,000 meters here, so that we end up with an angle of 4 degrees, 51 arc minutes. We get a elevation derived from the occlusion timing with the true position with respect to the mountain peak of 19 meters in difference and 230 in distance. For the glob, they get 18 meters in elevation for their terrestrial refracted angle, and 200 meters off in distance for their for the same. And then for the celestial refracted, 14 meters and 170 off in distance. For the raw globe, using the 180 times the distance, they're 22 off and 160 off, or 260 off in distance. So pretty similar there. And when we get to the spherical trig there, they're pretty much dead on. And let's see here. Well, but when we look at the refraction here, the lift, what we get for lift over distance, 49 meters. They predict 21. Oh no, they doubled it again. Son of a gun. They predicted 21 meters in drop, and they doubled it again, making the refracted position closer to what the flat Earth prediction would be for that location, giving the accurate comparison, the indistinguishable comparisons there. So we get another draw for the for the true position versus the optical, and then for the external consistency, we get another draw there because the distance is indistinguishable between the two. So given all the data that we saw, where we showed geometric failures of the globe, instances where the refraction correction was what it was because it absolutely had to be, where it's double, tripling, or equal to the amount of expected drop over distance. We have not verified a single drop over distance measurement, we haven't derived a single elevation or distance that corresponds to what the globe would actually predict in order for us to falsify anything here in terms of our null hypothesis. So real quick to kind of show what happened here is, oh, nice. They snap together. I can just do that. Is that a thing? Little snappy snaps?
Grouped them.
Oh, nice. Now they all change as a ratio to one another, perhaps? Ooh, nice. Okay, so we predict a larger triangle. They have a smaller they predict a smaller triangle. When we derive things based off of the occlusion timings to see what size triangle represents reality the best, we're finding that the flat Earth triangle, the triangle that represents a higher elevation, is the one that represents reality the best, because the lower elevation one never produces a result that deviates from the flat Earth such that we're off by so much. It has to be a globe. We actually run into areas where it's the opposite, where their refraction correction amount hits a threshold where they're like, look, we can only lift 1,500 meters, but we got another 200 meters to go. So we're actually now geometrically off by 200 meters. So we ran into instances like that. We didn't run into a single instance where that happened on the reverse, where the globe just produced a measurement where we were just so high off that it was preposterous. We're always within a tolerance of what the globe predicts for an indistinguishable amount there. So we have a nice data set here that illustrates a wide range of measurements that show that the globe exists of a ratio where the celestial refraction is equal to double or triple the amount of expected drop over distance, making it indistinguishable on most cases optically.
The globe exists in the math only. Is that what you're saying?
Yeah, because when you do it raw for raw on that analysis, they conclusively lose. And the big point about doing it raw for raw is because refraction on this side of the mountain ain't going to help you. Once you don't see the mountain, that's it. The mountain's, what time was it? Oh, that time corresponds to this angle. Okay, well, let's do some trig off of this angle and see what values we get for elevation. See what values we get for distance. Let's compare them to what the known values are and see which one's closer. And the geometric globe doesn't exist. The only thing that appears to exist is this refracted globe that has, without this external audit of the system, has an unfalsifiable amount of refraction that will always compensate for the curvature, such that you can't tell the difference between a flat Earth and a globe. Any questions, comments, recommendations? Oh, and before we do that real quick though, shout out to everyone who's helped put this spreadsheet together. A lot of people have contributed. I'm not going to name any names specifically, because if I forget one person, I'll feel bad. But shout out to everyone. You guys know who you are. And if you guys have any suggestions or comments, or your spreadsheet wizards, feel free to send me suggestions. And we'll get this thing improved and get it more digestible, and we'll get graphs, and we'll have things more easily represented so we can show these distinctions.
So way back at the beginning, you pointed out, of course, in the lower left, columns A and B, do you have a, quote, legend? And I think that is something that you really should expand on. And frankly, it should have its own tab. And every last piece of, every time you use a variable, just like you're explaining in these 10, 11-ish rows worth of legend explanation, I think they should all be expanded out and write 50 to 100 words on each one of those as necessary. You know what I mean? That it should have its own tab. And even thinking in the exalted spreadsheet God-like manner, get into the hover function where you're hovering over the variables on just the Pikes Peak sheet. So you have sheet 1, which is your legend expanded beyond what you have here, with full-on verbiage, breaking down each variable, each symbol that you use. And then when you go to the Pikes Peak page and you're looking at them in use applied to the formulae, and you hover over something that looks like Aries, Delta, Mountain, Alt.
Oh, no way. That's a thing.
When
You can do
hover
that?
over it, then that explanation from the previous tab page will pop up as you hover over it, and you can be reminded of what you're looking at. Just try that with the Pikes Peak page, and the rest of them is redundant. You know what I mean? And that would definitely improve the approachability for the newbie to come in and see and mentally interrelate what's really going on that page.
Oh, dude, I did not know that was an option. That is exactly what's needed. But yes, I will definitely do that.
Well, I did mention exaltation.
Yes. Yes, I want
So
it to be.
that's really what we're doing.
Yeah,
You know?
awesome, dude.
Yeah,
Great,
man, do that
great
thing.
suggestion. Thank you. Will do. Shane, what Stone just said? Do you incorporate that into the next
Make it
iteration?
so.
Make it happen.
Cover text hints. Got it. No problem.
Yeah.
And we have the chat saying Stone is 100% correct here. More explanations of the basics is essential for the uninitiated.
Yes, sir. It absolutely is, and that's why I'm gathering all the data, putting it in. So yeah, putting all this and making it accessible so that somebody could just have a sheet here they can read. Okay, this means that. They could look at the variable. They can go to the graph. This is what this is all gonna turn into. So thank you, everyone who's contributed to that. All right. Are there or were there any questions in the chat, like in particular about anything while I was going through
I
that?
did see one super chat go by, but you may selectively choose to ignore it upon your circumspection.
Oh, we got a soupy. Let's see here. How do I see?
Oh, I'd ignore it.
See soupies. What do we got here? Fan funding. Let's see. Oh, the final debate, 3 p.m. Eastern. Look it up. Come and show your proofs. Yes, we will be there to show the celestial theodolite. We will be there to present mutually exclusive evidence that does not falsify the null hypothesis. The idea that the sun being observed 24 hours in Antarctica is just the observation alone with no terrestrial or celestial intersections, like, tells us nothing. That's, I can point to the Japanese in the 1800s who have a working geocentric flat earth model, that they showed at the World Fair. So we will definitely be there to present our flat earth evidence. So save the date, boys, or whatever they say.
Rockin'. Okay.
And thank you for the $5. Much appreciated. All proceeds go to Cami. So if you guys want to support the legacy of Bob Nodell, you definitely send a super in and we will read your message. All right. Well, if there are no further questions.
Even if there are further questions after we finish wrapping up here, other people could maybe even add to the comments below the video afterward. We could maybe recap at the beginning of next Sunday and say, all right, follow up. These were the questions that were asked after we finished the broadcast, and here's our response. And then we move on to the new subject.
I do definitely check the comments afterwards. I don't know if anyone else does.
Cool, man. Now and again.
Yep.
Yep. All right. So with that, I think we can wrap up for the week. Thanks everyone for tuning in. Much appreciated. And Cami, what do you got coming up this week?
Well, actually, I'm just getting better. I've been a little bit under the weather and just working on getting better and getting strong. We have a festival coming up here in October. Karen, do you have something you can play for that, or
Is it on
not
the
cute if
website?
you're busy?
Is it on esoterica.world?
It is on esoterica.world. Also, BioCharisma, let me drop it into the chat here. BioCharisma just dropped a podcast that I have not listened to yet. He dropped it before and I haven't seen it again. I've been a little bit under the weather this week, but Pet Rock with Cami Nodell on the BioCharisma, we are talking about rocks, blood types, magnetics, just about everything that you're not talking about here on the show. So we don't do math on that one. We do have a lot of fun just with some all kinds of different topics. And so I dropped that in the main chat for anybody that might want to check out the podcast with BioCharisma. He does all kinds of fun things. He builds geodomes and incorporates magnetics in just about everything, in healing and growing plants and building. And again, just a neat way to look at things.
Awesome, dude. That sounds great. And I put the link for esoterica.world in the chat. So get your tickets now for some awesome esotericing. Karen, what do you got coming up this week? I imagine, I'm not a psychic or anything, but I imagine you have a show coming up that involves coffee and talking, perhaps?
As usual, every moon day, coffee
Nice, nice.
talk.
Every moon day, coffee talk.
Every moon day, yes, at 9:30 a.m. Eastern, and you can call in. Sometimes I make a link where you can join on video, depending on what's going on that day. And I just talk about current events and stuff that's going on, and people are free to join in that conversation and add to it, which is always fun.
Awesome. And from my understanding, Shane's been watching it every Monday since the last like 6 or 7 months now, Shane?
Yeah, it's been very good at work to listen to people not talk retarded nonsense, right? Which is what I get a lot during the day at work. So it's like a nice refresher.
I get a lot of that. A lot of people tell me they listen during work on Monday mornings.
Nice.
It kind of highlights my Monday at work for sure.
Nice. All right. Well, make sure to check out Karen B's channel and the Coffee Talk Show. ManofStone, what do you got coming up this week, my good sir?
Oh, I don't know if it's all going to happen in a week, but I got 3 things on the front burners now. And one of them is just off the top of my head. It's a spontaneous urge to put a new tune together.
Ooh,
Dedicating one to the trolls. That's all I'm saying there.
One for the boys.
And I've also had one on the back burner for a couple of months, hoping I don't have to make it. But it's a nasty video. It's going to come out a little bit flavored, somewhat robot polisher-y, I think, by the time I'm done making it. But it's a nasty video about somebody who does not think he should be held accountable for his actions and statements. And it's not going to be pleasurable, but I guess it needs to be made and needs to be out there just to up the awareness in the community. Third point was that for me, I think it's time to depart from BitChute, and I think I might be doing a little migration over to Rumble. And of course, I will be christening that channel with the 2 videos I just mentioned.
Awesome. Ooh, a nice little premiere. Are we going to have to do a premiere session or what?
Just to keep it round. Yeah, it'll most likely end up in a party on Discord. You know how we like that part. That's all the fun.
Awesome.
For
awesome.
sure.
Fantastic. Shane, what do you got coming up this week, my good sir?
Well, we got this going on Tuesday, probably more so Theo, and then whatever we're doing next week. I think we got a GLOBEBUSTERS presentation next Sunday for the 2-sphere model, maybe? Is that what we're scheduling?
It is your turn, my good sir.
Right.
So yeah,
that'll be fun.
Continuing the celestial sphere saga, because what we just learned about is how to externally and internally test the old celestial sphere to try and determine the shape of the Earth. And what we found was there's not a lot of ball drop, but there certainly is a lot of ball lift. Isn't isn't that crazy, dude? They're just
That's ironic.
Surprisingly, there's an equal amount of ball lift, or twice the amount of ball lift, or even 3 times as much ball lift as one would expect. Dude, that's insane. I can't believe that, man. They're like, no, it's definitely a ball. What's going on out there? It's just something's making it super flat forever. I don't know. Anyway, don't look over there. All right, so coming up this week for us for Ether Cause, we have Celestial Theodolite update number 14, where I'll be going over the spreadsheet again with the boys on Telegram or on Discord on Earth Awakenings. So join us over there if you want to ask questions live or be a part of the discussion. You can see what the lads are up to over there. We'll be doing that at 8 p.m. Eastern. And then Tuesday, we have Ether Roundtable number 94 or number 95. Not sure what that's going to be on. Inshallah, Shane has a presentation in between now and Tuesday to do. If not, we'll see what happens, boys. Not going to make any promises. And then, let's see. I think Saturday we have trivia hosted by Andrew B., who used to host a lot of Flat Earth trivia and charity events. So he's going to be hosting an Ether Cause trivia where you can win a t-shirt, t-shirt and hat prizes depending on your placement in the trivia thing. So if you guys want some limited edition Ether Cause merch that's left over from our merch launch, we're doing prizes for those, and we'll send those out. So how to participate to that? There's a thing on my YouTube page in the community section. You can follow the post there to join the Discord, and that'll be at 11 p.m. on Saturday. And
Can't wait.
Stone is our resident champion for trivia.
Trivia guru. That's the word. Yeah.
All
Not
right.
surprising me. I hear rumors you're a Scorpio. They're stoned, so that
Me?
would be yeah.
Yeah. Would you believe
Yeah.
a double Scorpio rising? Yeah,
I
it's
would
pretty scary
believe it.
on this side of the fence.
Oh, look at this. We have them talking astrology, Karen. We're already
Here
half of
and
the way there.
My wife is heavily into astrology, so I've had a thorough exposure to that.
What month was your wife born in?
Oh, she's a Taurus.
She's a Taurus. You have a Taurus Scorpio mix. That should be
That's
spicy.
what me and Ted
Yeah, it's
are.
interesting. It is interesting. I think part of it actually has led to its longevity, frankly.
Mhm.
Well, Scorpio and Taurus is opposites. That's, they're a good match. Ted and I are Taurus and Scorpio. He's the Scorpio.
Bob was a Scorpio. Bob was
Yeah.
Oh,
a
yeah.
straight on Scorpio too. Yeah.
All right, lads and ladettes, we will
All
wrap
right.
up here.
Shane and Alan aren't
See you
playing,
guys
so
next
okay.
week.
NA.
Not a classic. Love it. All right, you guys have a great week.